Chapter 4, Gravity, Projectiles, and Satellites. Section 4.1, the Universal Law of Gravity. So up to this point, we've talked about gravity, but we haven't really talked about how to describe it. We've talked about how it causes things to fall, but we haven't really talked about why it does that, or what's the magnitude of a force on something as it's falling. And that's part of what the beginning of this chapter will be about. Towards the end of the chapter, we'll expand on the idea of gravity and talk about how it leads us to understand how other things move. But in general, the story of gravity goes back to Newton, right? So the story goes, Newton was sitting under an apple tree, thinking about the universe, an apple falls on his head, and he realized that something had to have pulled the apple down to the ground. And so Newton figures, okay, well, if the apple is pulled to the earth, right, then maybe there's something that holds the moon to the earth. And from that, he eventually came up with his idea of the universal law of gravitation. The universal law of gravitation just says that all objects that have mass experience some force due to other objects with mass. That force is proportional to the product of the masses and inversely proportional to the distance, or to the square of the distance between them. So what that means is that you have more mass, you have a greater gravitational force. But it also just means that if you have two objects with mass, there's a gravitational force between them. It does not matter what two objects those things are or how far apart they are. That gravitational force still exists. It could be really, really small, but it is not zero. Now, there's something missing from this description of gravity, and it's primarily an equal sign, right? Newton was able to figure out that the force of gravity was proportional to the masses of the objects and inversely proportional to the distance between them squared. But he could not put a number on it because there was no conceivable way to figure out how you then go from that obvious proportionality to directly calculating a number that represents the force. So in the early 1900s, a guy by the name of Henry Cavendish decided to come up with an experiment that would allow him to essentially measure that missing piece of the gravitational force. And what he measured was what was known as the universal gravitational constant. We write this one with an uppercase G. It is different from a lowercase g. That's gravitational acceleration. They are related, but they're not the same thing. The magnitude of the universal gravitational constant is the force between two 1 kilogram masses that are separated by 1 meter. And as you can see, that force is really, really small, 6.67 times 10 to the minus 11. So a decimal point with 10 zeros before you get to that first 6. So really, really small value. So obviously hard for Newton to figure out and hard for him to measure. It took until you had more expert measuring techniques to figure this out. In my time in college, I did Cavendish's experiment, and it is incredibly, incredibly hard to do, to get that accurate. But you can visibly see gravity occurring during Cavendish's experiment, whereas you don't see it necessarily on Earth. On Earth, when we think of gravity, we think of things falling to the ground. We don't think of two objects being pulled together. But that's what happens. And there's another video that's with this section where you can physically see it. Not the best video in the world, but you can see how masses will pull towards one another, and it does not have to be being pulled down towards the earth. So gravity is one of what's known as the 4 fundamental forces in nature. Gravity is by far the weakest of those forces. The other 3 are the electromagnetic force, which we may discuss a little later, but also the strong and weak nuclear forces, which we won't discuss at all. But though gravity is the weakest of the forces, it is what holds planets and the solar system together. It extends throughout the entirety of space, and anything will experience gravitational force from anything else that has mass. So when you have large masses, it's readily apparent that gravity exists. Without gravity, the Earth would just wander off into space, away from the sun. When we're talking about ourselves, the force of gravity that we experience on ourselves is our weight. The weight that we experience is gravity pulling down on us from the Earth. And so, just by understanding the gravitational force and the gravitational constant, we were able to as scientists determined the mass of the Earth long before the entire Earth had ever been fully discovered or explored. And in some cases, parts of the Earth, especially under the ocean, still haven't been explored. But we can calculate the mass of the Earth because we know how much it pulls down on stuff, particularly us and other things, particularly things like satellites. And if we were inaccurate about that, things like satellites wouldn't work. And that's what you'll see in later sections.